Okay.
Yeah. C'est normal, ça? Enfin, ah, no, don't move it too much.
Okay.
It's,
Sure. Sure. Okay.
Et peut-être,
c'est bon. Tu me dis, c'est bon?
ouais, on a 5 personnes en ligne. Je pense que pour un vendredi, ça va être pas mal ça. Fait que merci d'être présent.
Good for
On a un invité, puis je vais laisser Jérôme faire l'introduction.
C'est bon. Donc, bienvenue à tous. Donc, aujourd'hui, on reçoit Gunho Sohn, qui est professeur à l'Université de York, qui est directeur du département de la science de la Terre et de l'espace et de génie, directeur du Centre de mobilité et d'innovation, directeur du laboratoire de modélisation augmentée de l'espace urbain. Je fais une traduction libre en direct. Merci d'être venu, d'avoir accepté l'invitation. Et puis,
Okay.
à ton...
Yeah,
Je te laisse la parole.
Okay.
C'est bon.
Is it okay? I can speak in French, but can I do in English?
Yeah.
Okay. Thank you so much. Well, thanks for having me here, and I'm glad to meet. It's really glad to meet all the friends and visiting same school. I love it. And so what I'm going to tell, and how many people are logging online is
6.
okay. So I'm going to talking about several research works that I've done over 4 or 5 years through I think a 2-3 projects. But the sum, and I hopefully this presentations will be helpful and informative to you. What I'm going to talk about today is the urban digital twin. I think anyone heard about it? Digital twin? Okay, right. It's a sort of not an academic term. It's more sort of like an industrial, terminal, which I have been closely working with and recently, and I'm much behind in terms of digitalizations. Although they, when they start the constructions and managing the bridges, dams, and they relies on certain informations and a CAD and that sort of thing, measurements and digitalized information. However, it is not completely tightly, embedded in their everyday workflows. Very much behind, compared to other industries like mechanicals, aerospace, and other, because it's nature of their scale of the project they deal with is very complicated, very large scale, and so many stakeholders are involved in. So it's very much problematic for just the simulating steps and predicting steps, and in a very short period of time is impossible. So as you can read here, is construction field is one of the key factors for producing the carbon emissions. So they discuss a lot of things and how they can be more dealing with these issues, challenging issues. One of the ideas is digital twin. Particularly, idea is to transfer reality of environments built environments into the digitalized information, and where DNA and data network and artificial intelligence can be integratable within that digital form, and hoping that they can more streaming digital informations about the monitoring their health and a status, and even they can embed it sort of physical simulation body in it, so that so this realities and virtual reality can communicate each other, and avoiding a lot of simulations with the physical contents. So certain successful project can tell in this urban digital twin can improve the efficiency and productivity, even make our systems more sustainable. So, and ideas about the life cycle of the management of this big environment. And so one part of it, and I think there's numbers of process that we deal with. And the first one is how we're going to transfer natural and environmental information into certain forms of digital information. And then how we're going to integrate it in a lot of sensors, which becomes cheaper and cheaper and more energy efficient and more sustainable. And therefore we can stream the more information out of it. And that can help like a sort of simulations, understanding their status. And also a lot of buildings and bridges, 1,000 of them, how are we going to federalizing it so that not only just one management of one asset in a, the bigger scale of the urban process, how can we optimizing their performance? And at the end, ultimately, and autonomously make a decisions, not rely on the humans, more augmented human intelligence, that we can make better decisions and based on these sensors and networks and artificial intelligence. For achieving this goal, if this hypothetical assumption is right, and the first part is the digitalizing these big environments like trees, land, waters that you everyday walking and studying now, it is important. But what I'm going to talk about today is that just the data acquisitions and using the drones and using the devices in a populated reality with certain form in a point cloud, that is not enough. Data acquisition is not always enough. I can tell you why. So this is a sort of a very small toy kind of workflows, and given any input, and you can populate it optical, point clouds and laser point cloud, and then we're going to translate it into certain forms, and that is a optimal and suitable for embedding, integrating your artificial intelligence or the sensors in it. So we do not want to know what the point status is. We want to know certain semantic areas and sections of the beams and cross sections, and certain engineering part is important for communicating between sensors and this digitalized form. So therefore, my argument is that all this point cloud translated into, and for me, the abstract representations and geometric forms, that will be more important and critical for achieving this urban digitizing. This is one of the example, and so this is FSO, it's a big ships. So autonomous drone is fly over these big ships, populate its point cloud in a day. These days is a commodity. Is getting this big point cloud represented reality is not a problem. But what engineering actually want to do is, more than a month they spend the time for translating this point cloud into this a certain, the structural body. So that is how they built this asset, and also they want to manage it. Certain cracks and rust that happen, then they want to know quantifying them, not just based on point, based on the semantically interpretable, geometrically understandable engineering forms, right? So, so therefore, it is very important for into this. That's what we call the 1-to-10 ratio. So 1 month you spend for data acquisition, 10 months it spends for translating it. So we're hoping that artificial intelligence, more intelligence mobile mapping system can help to reduce this 1-to-10 ratios of data acquisition. That's what I'm going to talk about. So one of the examples that we had in York University, and we targeted to sort of meet the carbon emissions and lower down them 30% in certain times by 2030. I spent like 4 years and then translate entire campus. And we are the third largest campus, the 60,000 people. We have 2 subway stations inside the campus. It's very big. And we converted into 90 buildings into digital inside and outside. and 6,000 trees and the roads, and almost everything is digitalized. It's not still completed, but it's quite heavy campus this twin we built, and using it as platform for mobility studies, and now I'm leading it, and as a director of the the Mobility Innovation Center, and also working closely with electrical engineers for sensor networking and threaded to minings and civil folks. So this is one example. Is we AI is the automatically extracted hit points of your gate, and then this virtually geolocated this human's positions into real scale of the positions, and then we analyzing the gate analysis. And the right side is we trying to using this digital twin for understanding how. So I don't know what's happening in Sherbrooke, but in Toronto, the city council and a band not allowed to deploying the robot on the street. And so because they're worrying about, and they still don't know what danger might be impacted to mobility vulnerable people, like elderly peoples and disabled people. Even though the sidewalk robot is very slowly moving, so there's no policy implemented. So we're trying to simulated it based on digital twins and deploying the sidewalk robots. We keep changing it. We deploy in pedestrians. So how they can harmonically, they're working together and preserving the safety of them. So this is one of the example, and this is another one. We exit entrance controls and pedestrian, deploy, and one sort of ad hoc routing, and particularly under COVID time, and the jointly optimize the pedestrian mobility efficiency as well as safety. So then we keep changing, controlling the exit and the entrance and the route, and then they see what sort of factors coming out, and then we analyze the optimal route for them. So as I said, from the point cloud and translate it into geometric map, so georeference correctly, and all semantic map, or representing them into the primitive map, would be very critical for achieving this goal. You can see now. So today, what I'm going to talk is there's several topics I'm going on in my labs, but since I have been working with drones on Patrick's about the drones, and maybe you might be interested in how our drone research is going to get advanced, what's going on now, but very few. Okay, so we're thinking about the Q drones, the quality. What it stands for is quality drones, and autonomous drone these days, and they're trying to avoid obstacle. That's one primary goal when they deploy it, and they trying to get to the destinations. And one goal is not hit the obstacle. For us, is we need a secondary but more important goal is why are they moving around, and what about the quality of the mapping quality? So why are they avoiding the obstacle as well as the make sure all the 3D point cloud captured well, and regardless of the detail of the structure. So that's what we call the Q-drone system. And the first step of this Q-drone system, and actually Patrick is making the second version, and we attached UWB ultra wideband and sort of the range transmit wide band of radio frequencies from the one anchor to the small drone system. We have four of them. So if you're given a range, and we have a small IMU devices which can tell your orientation. So we sort of understanding, and when we receive this signal, and actually where the drone position is. It is not very accurate enough, but that's actually giving it an idea, right? How far and where oriented. So in time to time we receive, and we estimate the position of the drone, but how are we going to improve and the position accuracy? So idea is, we have the not only the 1 and 3 or 4 and triangulate them, then we gain to getting the positions of the drone as well. So the question is, we have 2 different way of estimated positions. How are we going to put together into certain types of mathematical form we call the vector graph? So this is the single range, and how we determine the positions, and this is triangulations. And these tools are avoiding the conflict about the probability distributions, but to safely inject it too. And idea is that we're using this triangulation as hard constraint when we introduced it, and then we remove the single range one. So basically, we calculate it based on this, and at certain times we rely on this for correcting it. So that is the one idea of it, and I'm going to show the videos. And then now the second after that, and the second phase is and we introduced the drone at the AI in it. So artificial intelligence, as you know, they can tell something, predict, and with a certain probability. It doesn't mean that their answer or prediction is correct. So let's say I could tell you are the humans, and as in intelligence point of view, with a confidence level of 98, it's very strong confidence. It doesn't mean that your answer is right. Someone is arguing very confidently, but someone can be wrong. So what we're trying to do is we're trying to predict and train the networks to predict the uncertainty and rather than probability only. So this network is, we call the LSTMs and VA. You don't need to know, as everything is available. We designed it, and which allows you to 2 jobs. And one is, and they smoothing the noises. That is one branch is we ask it to do it. The second one is they actually, when they predicted it, and tell me uncertainty. This uncertainty is important for any mathematical optimizations. So that is going to be injected the same and the networks that you saw here. So before how we did, manufacturer can tell you in all the range this is a standard deviations. But now we can able to predict standard deviations every single ranges, and that dynamic ranges can improve. That's our hypothetical problem formulation. Now, the baseline post graph, the system that you saw before versus this is the AI-based one. So the previous one we achieved in about the 25 centimeters to 30 centimeter accuracy. And now with AI enhanced one, and we now can achieve and quite a lot, right? And 15 centimeters to the 20 centimeters, that's what accuracy we can. So we're so excited about, and because list scale adjustments, whatever mathematical optimizers, they need a standard deviations to be minimizing it, and for optimizing parameters involved in, right? So how we can train the networks for predicting the uncertainty through the neural networks is, if it is possible and easy to implement it, then we can use this to optimizing many different things. So it's exciting things we found. We just submitted to in ICRA 2023. So this is sort of the result that you see now. And again, Patrick's and his movement a lot. I don't know, you remember it?
It's been a long time.
Yeah, so we were here and they collected it, isn't it, right? And so CGQ is involved in, so under bridges, inside a tunnel, near buildings, open field, and indoors. So GPS denied, and also UWB multiplexed it, and from the glasses, and how, regardless of all this noise environment, how the position is going to be affected. So you see, the red dot is represent the, I think the estimated one, the ground truth. So we place the prism, and then robotic total stations can track or collect the ground truth. And blue is our estimation region. So if you see not much deviations between the blue and red, because the error is small, right? So that's the idea of it. So we're very proud of sharing, releasing this Q-drum benchmark data set. So quite a bit of people now downloaded, they're testing their algorithm. So you can find it out the data set from our website. So far okay. Any questions? This is very informal. Any questions? To check my. Any questions so far? Nothing related to? Okay. Now I'm going to move to another types of mobile mapping system. Again, and I'm going to present how we utilize AI versus internet for solving this particular problem. So the SLAM means, as I said, the point cloud and generating point cloud is important. And however, well located them it is also very important, and georeferencing them. And so what we're trying to do is this, the mobile mapping system, and this is Maverick, and from the Teledyne Optech, and which used for we have a tilted laser scanner and also panoramic 360-degree cameras. So this is panoramic cameras you see. This is the tilted laser scanner. So this device is different from autonomous driving car in a way that autonomous driving car, they cares about and not hitting the pedestrians and trees and on the street. So therefore, the laser horizontal field of view, panoramic field of view are the same, right? So they want to aligning already between the cameras and laser. But mapping, however, the panoramic is important wide horizontal view for texture mapping. But laser, we need to scan the underneath of the bridges, ceilings and tunnels, and reaching to the higher building facade. So therefore, they prefer to they have to tilt the laser scanner. So what happened is now you see this is panoramic image, and this is a laser horizontal view. This is not overlap very well, and so under this, the sensor configuration built mainly for the mapping, then this company is interested in, and they also they navigated well and georeferencing them well under GPS denied environments like a downtown Toronto, and it's a big buildings, so the GPS signal is blocked, and then they easily lose their GPS signals, and therefore it's a bit of a problem for georeferencing them. So that's the problem that we had, and our answer is that so this is very sparse in a point density. It's not a continuous space, right? So then a lot of this little green guys is very important for locating the position of this people. So it is important to increase the density of this point within it, right? And the challenging is laser is discrete point. It's not a continuous space, so that therefore it is likely to lose in a green point. If so, then they impact negatively in accuracy of position. So given this discrete laser point cloud, and we interpolate them, so to make a more, this range depth is more continuous space we translate it into. Then using this in masculizing, and then using it for matching more points. That's a simple idea, but effectively working well. So this prototype is built. Now the question is, how are we going to replace this very naive way of interpolations with an AI? So our answer is, this is depth estimation in the AI community. So it's not only me, it's many people walking around and seeing the image and predicting the depth. But this depth is relative scale, it's up to scale. It's not, they can actually tell you exact depth, right? So however, it's working well. So given this panoramic image, this is existing AI networks and educated for predicting the depth. So it can tell you, and after this, you injected it, it can generate the depth. And then interesting part that we designed it, is the dynamic domain adaptations. I will tell you what it is. So this network is what you see now is working in real time. It's phase, not the training phase, right? So I will tell you one by one, and hopefully it makes sense to you. So the camera's input and the depth is estimated like this. We using the laser in real time as our ground truth. So network can predict the depth based on an image. And now my friend's laser, and they make a comparison between depth predicted from the cameras and laser in a real time. So we assume that there are some gaps between the camera-based depth estimations and laser. That the discrepancy is going backward and like backpropagated in the networks. And we actually changing the feature and in a scale factors bias. What this means is this RGB and is images pixel by pixel are translated into and certain values. So we call the latent variable. That latent variable is somehow encoding the information about depth. So if we just multiply A, this whole feature space, plus B, the scale factor is bias, then this network actually can predict the different things. So what we're trying to do is, and in the real time, and measuring the differences between cameras and laser depths, and then backpropagate it, and then we estimated the scale factors and bias iteratively until the camera depth is close to the laser depth. So that happening in the real time. So that's worked very nicely. So then that's the what we're saying is that using this AI enhanced SLAM, and that's ATPV SLAM, and actually giving quite a bit of, this is the company's, the commercial solutions, and absolute and translation error is very, very high because this is the under like perform the environment and challenging environment. This is the relative translation error. This is the relative orientation error. So compared to what the company's pipeline solutions versus our previous one, and without the AI versus this is the AI versus one. Okay, so that's the what we achieved now. So that's the so far what we've done in a couple of years now. So this is the Paladin Optic, company's headquarters. So this is the ground truth trajectory, and this is the estimated trajectory, and based on AI enhanced positioning. So that this is what it looks like. This is York University inside the campus. So speed up the story about this whole region is not aligned angle mistakenly, but you can figure it out the which one is related. So it's quite well aligned with each other. So without using GPS at all. So it's just a totally cameras laser. That's the whole without using the IMUs and GPS is quite happy about what we're doing. This is residential areas near to York University, right? So I can skip it. But this is sort of an autonomous mapping system that we've done and with the companies. And this company also has this is 4 years program. It's very big scale. So one is the improving their mapping system, and the second part is their AI-based solution. So the company is a geospatial company and aircraft with laser scanners and mobile laser scanners. So they want to process the semantic point cloud better and also modeling better. So I'm going to show something that one of the things that we just published and about the point cloud segmentation. Any questions related to mobile mapping system so far? No? Okay. I'm going to talk about one and a research project done by Jacob Yu in the lab. And we just presented it in Vancouver, CDPR, and the workshops, and we called INET. So I can tell you what the problem is. The goal is and given a point cloud XYZ, and network predicting the semantic categories like buildings and roads and trees and grasses and that sort of stuff. So laser point cloud is the getting a denser and denser and denser. And so AI community and the mainstream of computer vision communities, they're not dealing with the aircraft-based one and autonomous drivings and sparsely just point cloud. But our cases is very, very dense point cloud comes in. So network can tell in educated based on how much information injected as a input. So what they do is because the GPU has a memory limitations and a lot of problems and scale up. Given 40 million point cloud as an example, they actually downsample 3 million. It's like a 50 centimeter by 50 centimeter. They pick up the 1 point for training the networks, right? So this is the state of the art in today's practice. So 40 million down to 3 million grid sampling, a lot of sampling technology introduced. This looks okay, but still is not enough. The question is, this is this geospatial size of the input. So we call the batch. So you have a networks and input size, we could not like a entire data set introduced to the networks. It's only a small part of it. As I said, the technical limitations, like memories and computational limitations. So this input 1, 2, 3, 4, that is a sort of the real scale of how network actually see and understanding and educated to predict the semantic labels. The problem is that this is what actually the network see. This is the very flat, but that is in the middle of the building roof. Looks like a terrain, isn't it? And this is ground, this is roof, and this is parking lot, this is road. So if we understand the road, we look at the trees nearby and people passing by, and we contextual information is very important for understanding it. Because of limited distance input size and network is not very well educated or losing some chances to memorize the contextual relationship between an object because of scale. So what we try to do is going back to the human eyes, and we have receptors in a certain neurons, right? And we have retinas. But density of receptor of human visions is different. So we have a very, very high density of receptor in the center of your eyes. But when you, moving away from the center to the edges, you have a lesser density of the receptors. They help each other, but these peripheral visions and move away from the central visions. And with a very small, lesser density of receptors, they cannot see like a detail of the shapes or geometry, but they can retrieve a certain amount of the vision, cognitive vision informations, can help to understand these focused visions, right? So we sort of getting these ideas from this human vision system. So what we're trying to do is we're trying to this black box is a supple is sort of mimicking like a peripheral vision area, and inside, and that is a central vision area. So we keep the raw density, like a high density, and within here, and outside we have a very sparse density. So which allows you, and the state of the art in exercise, and when they created input size, we keep the same input size, but you can actually increase the scale of it, right? So that's the questions about it. So we keep this inside the yellowish, that's the central vision part, and we have the blue, the peripheral vision part, which we sampling at different density, and we injected it clusters into the networks as an input. But remember, and the integrated and density itself is equivalent to the higher density and with the smaller radius. So So this is a sort of ideas in behind these problems. So more detail, and so this central part in it, and this is part of peripheral, isn't it? And shared in a core part, and they drive the features, they combine together. However, the peripheral part is they actually separately features are extracted. Later, in a central part, in a peripheral, what they see is combined together like a human vision, and then they can actually tell what is it. Hoping that our hypothesis that this increasing the scale with the peripheral and can tell like some sort of a contextual informations. And so that's the state of the art in today's, and Randall is from Oxford in a plus, and our is actually showing the couple few percentage of improvement, and that is sort of presented in the CBPR in this year Vancouver, right? Okay. Okay, questions? No. Right. It's good. Okay. Like 12 minutes. Any questions? Problem? That's good. So you can find it out paper, and I will be around here, and then you can have questions. Please let me know. So this is a sort of the ground truth here, and this is INET. It's different names in appearing here, but you see this is the Oxford and Randall networks, and as I said, this is errors because in the middle of the room, and they consider it as a cars and as things. So it's a sort of a lack of a scale, the context. That's why they confused about the semantic labeling. However, we do not see that sort of problems much. Likewise, and lots of more details errors we can actually smooth it out. So we believe that is benefit from scaling up the receptive field from the beginning with a different density. That's what we want to do. So what the benefits as conclusion, and the network requires only 1/4 points to ensure comprehensive coverage area, and compared to NDLA. And then inference time is 25% shorter than other state of the art. And so that is sort of efficiencies and accuracy improved based on these networks. Okay. So is it okay now?
Yeah, there was a question online from Mia.
Mia, okay.
Yes.
Okay.
Hi, Gunho. Thank you very much for this presentation, especially for this part. I have a question in terms of applying the same vision that you have in terms of mimicking human vision in this part of your studies. Would it be possible to integrate, let's say, instead of considering always points as a peripheric information that allows to integrate some contextual information in this study? Is it possible, for example, to use other source of data so that we can actually bring the same knowledge that supports a better segmentation of a point cloud in this sense?
Thanks for that question. The image domain, and people already studying a lot in the multi-receptive pills, and not exactly same question that we have. And so my very first answer is yes. It will be very interesting for us to apply it to image domain, and even both domains together. That would be very interesting. But I think the engineering-wise, and using the image, I think they have a relatively not difficult to scale up the input size. And what they, however, be more interested in it is given an input, then how receptive field, multi-scale receptive field applied it to for detecting or segmenting different size of an object. Make sense?
Yes. If we go further, if you allow me, just go 1 minute further. If we say that in human reasoning way of doing things, visual sensing is one of our capacity. So in our mind, we have a lot of knowledge about the environment. So
Yes.
even to say that that context could be multi-layer of knowledge, which is partly external and partly in our mental representation, so that we reason based on what we see and what we have already as a knowledge in a specific location. So that is a kind of pushing farther this kind of integration of supplementary information to the way we reason with AI in detecting objects or segmenting objects.
Sure. And I just thanks for bringing that up. And I want to talk about it to the students at the end of my presentation. Maybe better to say now.
Sure.
Yeah. So I already said it in an NRCan. AI becomes and will become soon in a commercial commodity. So then everybody can take it. And however, domain knowledge, like this department and students feel like knowledge is about water, knowledge about land and soils, and those knowledges, the specialized in the students and faculties, and then ourselves, right, and expertise in it. So how to integrate this domain knowledges and tightly couple with an AI network that's very interesting, Phil. And a couple of few physics, the researchers in the control theories and whatever, and they actually apply knowledge about our understanding of physics with an environment and how we're going to integrate it within the networks, mathematically and theoretically as engineering wise. I think a few people are already very actively leading it. So what I'm saying is that we sometimes over 10 years, we overwhelmed with an AI. But now it is a tool, and its question is how are we going to integrate our domain knowledge within it? That becomes more important.
Exactly.
So the students graduated, and then the AI studied computer science PhD. I don't think they will be very easy to differentiate it themselves in the market. But however, the domain knowledge, like us who studies the nature of things and environment, and also in understanding the AI as a tool, much better positions, I think. So that's what I continue to emphasize in the lab. Make sense?
Sure. Yeah, this in terms of perspective of this research, very interesting. Thank you.
Yeah, thank you. Right. So now I'm talking about another subject and given 15 to 20 minutes. And I'm working on a power line, working on the other types of segmentations, but this one is more about the 3D modeling. So this is my very long-term and research topic. Whoever PhD students, masters interested in, I continue to work on, side. So this is humans, and a 3D perception is very important. The depth estimation, as you saw now, and humans can avoid obstacles in reaching out things and grab some things based on this 3D perceptions. Even the abstract representation of 3D perceptions, like a model, right? Building models and road model, and that is much make it people's easier to work on it. But this is the very, the famous, the figure, and I think the David Mars who coined the machine vision. So he was the psychologist, cognitive vision scientist, and in the newspaper and a long time ago, and where not many photographs has been exchanged. And people keep hearing that hot dog machines in New York, and a lot of stories about it. And then David Mars asked the people, and based on the descriptions and reported in a newspaper about this machine, ask them to draw it. And this is sort of a people draw it. And so representing, the objects and graphically, and people relies on a simpler, generalized perceptions, right? And not very details and noise drawing, and they utilize a certain form of the primitives as a visual cues. So this is a sort of a central part of the cartography for me and computer vision. So that when we say that 3D modeling of the building or road, for me is more like an abstract shape representation and how we're going to do it. But it is really, really complicated problems, and we spend a lot of times in solving these problems, but this is really bad. But the why people want to do it, and 3 primitives more compact and more holistic and representing an object with a few parts and simplify the reasoning process. And for example, if I build a robot and ask them to grab some glasses or something like that, it's really hard to program it or educate a robot and what is a glass is. But if we can simplify the representation of glass with the geometry and these primitives, and then I think it's make our life much easier for implementing that tasks, right? So this is one tiny example. You can tell many examples why 3 primitives is important. But challenging for this model is so many hypotheses, like a hypothetical parameter space to explore for finding the solution is huge space, right? And so this is quite challenging in over many decades. So I'm showing certain types of interesting things that I'm working on. So I'm trying to build this pipeline many years and how populated in very large scale, not just 1,000s and few millions of them, right? And now it's a little bit happening. And also how are we going to continuously model? Like, the model is built, but urban built environments keep change. And how are we going to understand the changes? How are we going to reflect them and representing, the geometry over the time? And also make it interactable, right? And so this is by very long times, and this is very different school of thought in about the abstract representation, particularly for building, and one group of people saying that numbers of primitives is already given like a library, and then I'm going to represent my building based on the combination, like a selecting of this and fitting things, a combination of this given model. And the other people thinking that, I can drawing it from the bottom without knowing anything, right? So, and then I think both are having problems, and this one is limited and based on the numbers of primitives is given, and whether the accuracy of knowledge is A-priori knowledges. And this is challenging, and drawing everything from the bottoms. What about occlusion? What about the shadows? And so there's a lot of problem. So I'm trying to solve these problems make a balance between. So I think what I'm doing is I'm basically my foot is drawing the things from the bottom. And however, some sort of A-priori knowledge is also involved in it. And this is something that I'm going to show. Okay, right. So I'm represented the building as just a rectangle, right? And from the beginning. And then I don't think you're seeing very well. And the red line in a drawing, and then you actually end up with 2 shapes. It's a polygons, right? And one shape this and one shape the others, right? And then you can introduce another line, and then another line too. And then this, the initial shape of rectangle is now decomposed into set of the polyhedron. So this you can achieve it, and based on the computational algorithms such as bispatial, the binary space partitioning or others. And so it's a matter of which line is selected and how you divide it and how to combine them. So that's the optimization part. And then if you do so, and then you end up with a very nice scale of this. This is one of the real Toronto building. And so this is in 3D. So in the 3D is not a line, it's a plane, right? And given a point cloud, and I'm shaping in a cuboid things, and then one plane is introduced, the other plane is introduced, and sequentially and optimally, and then you end up with a very nice building like this. Okay, that's sort of one idea that we built many years ago in an in-house pipeline. So this is a sort of a scale of things, and we released a long time ago the benchmark through the ISPRs. Still is very popular. This is a sort of the scale that we built through that algorithm and in downtown Toronto. So after that, and still sort of a little noises comes in, and how we're going to modify them. So we introduced like a stochastic implicit regularizers. What it is, very noisy one, and then we continue to we reverse the very noisy lines that we can draw from the laser, and then we simplify them, and then much smaller numbers of lines left over. And then we stochastically, we move around these lines and vertices. You see now, I select, part of this point, and then this is one hypothesis representing local reasons with this model. And then I'm moving around, right, like this. And then I generated other shape representation. And likewise, I can move around these vertices and as many as possible with a certain row. And then this many hypothesis comes in that I produced. Likewise, you can select the other actors and then drawing the plot lines and then the shape lines, and then we can produce many of them. Likewise, you can introduce many things. Even you can remove it, right? So in this space, either you can merge the vertices, remove the vertices, and moving around, the numbers of hypotheses are generated. And now the question left over is which one is best? And you can do it as so in moving around entire shape reason, and globally, locally, you can optimize them. And this is one of the examples that animated to. I'm hoping that it's moving around. This is 3D in the same building. So a lot of noises now, and very slow though, because it's produces lots of hypotheses and optimizing it. And we don't care about computational things, but in just all the local reasons are generated hypotheses. What sort of we guiding them to be settled down with an optimum is that the gastroctic law kind of, peoples are more sensitive to see the orthogonality, the smaller vertices. And so all this optimizer is representing the same reason, minimum vertices, and minimum line distributions and slope distributions, acute angle. So that's sort of a priori analysis in it. And so with its stochastic populations, and it will help. But that is certain, without an AI, we did it in large scale modeling, and this is a really big building, 1,600 buildings are populated to. And then this is continuous modeling. So the given one building vector, same mechanism, but the lines are coming from the existing vector plus image and the new image or laser, and those are the lines is coming together, right? So then more lines introduced to the same mechanism, and then this is how they actually reconstructed it. So this is sort of ideas that how continuous modeling can be. So the numbers of things are generated depending on the galvanic vector's weight, and then sort of min-max things, and okay, this is would be the best shape, and then this is how we got. So this is all the benchmark and tested it, and so we sort of that's the performance we got in that times. This is sort of optical images, lasers, and this is what we produced as a building model. That's the without the building. And then once students comes and we study together, and then we participate in CBPRs, and this would be to take I took a 4th place in the competitions. And so this is the, okay, whatever the building detected it, and then this rectangle reasons, and then network is actually convert pixel by pixel intensity value into related variables, certain informations about the semantics. This is a building, this is non-building. And that feature vector is here, then within it, and then we initialize a building shape with the 16 vertices. So we create a circle with the 16. Now this connected graph, now let them dancing around. Like this, all these vertices can be moved delta x and delta y, and through this one networks, right? And then they move and then going back to, and then again they comparing the features and their moved initial shape, change the one, and then they move it again until they minimize all the losses. Okay, when they train is finished, and then we don't do any iteration, it's just building rectangles comes in and building vectors out in an inference space, right? That's what the we call the R poly-GCN. That's network. And these persons and I studied together, like when they pull in the probability with given a grid image, and usually grid space, pixel by pixel, they pull the probability as building, probabilities as non-building. But however, we studied before the binary state partitioning, like a polygonal hetero space. So we want to pull the probability not only from the grid and from the partition the reason, and then we want to combine them. So that is the sort of this all polyhedral things are divided, and then we pull the probability from them, and that's what the grid space versus, and this is BSP and binary space partition based feature map, and then we concatenate it, and then we pull out the final result. That is one. And then we continue to study this year's and last year, and trying to improve that building model there. We call the OCR poly-GCN. So basically, we tried. Well, the problem is the previous one is we too much relies on the semantic informations, right? In a building and non-building kind of informations. There's no geometric informations trained much. So what we're thinking is that we're asking them to predict the corner and also the orientation. So that corner is predicted, and then the orientation vector is also predicted. And then in the graph networks, they're trying to look at the same this conjugate the orientation corner. It might be the good matching, right? So we're trying to add more information about the geometry vectors, and that's what we changed this the networks. So whatever semantic networks that you use, and the semantic is coming out per building, and then we have 3 different tasks. One is the hey, you can predict the corner, and then also the orientation, and this is the masking out, right? And what is the building on? So within it, in the same algorithm, like initializing it and graph convolution neural networks, and iteratively they move X, Y. However, and what we guide them is, this is the good movement if this orientation, that orientation align together, looking each other, and that sort of information is more additive to, then this hypothesis is really good, really exciting about it. For example, this is orientations comes in, and this is the sort of, you cannot see much, but there are some trees, right? The trees occluded the building roof. If we just ask them to reconstruct the building roof only based on what they can see from the image, it might be, they cannot draw like this. But even though network cannot see the house because it is occluded by a tree. But however, we educate them this geometrical configuration regularity, so they actually can predict it, the corner, even under the tree. But that's the very exciting things that we found, and we sort of busy to write papers at the moment. So this is the quality, like corner is coming out, and this is the corner-based building. I think that this one is grounded truth. This is what our prediction. Likewise, this is the grounded truth. This is what our one. So this is the sort of a performance metrics we continue to work on. So this is something that we really excited about. Then ultimate goal is not just to build a footprint. We want to, continue to extend our researches to added to is a level of detail. It's basically roof structure, not the footprint. So then if we continue to use this oriented corner and graph convolution neural networks, and how we're going to extract the roof structure, that is the what we're trying to do now and onwards, right? So, okay, this is sort of, the last section of the my research works then. Okay. Any questions?